Hello again, everybody. Welcome back to some more lessons on electrochemistry. What we're going to do in this lesson is we're going to talk about how to balance oxidation-reduction reactions. Now, you might be thinking to yourself, hold on, I learned how to balance reactions back freshman year. And that's true. But when it comes to oxidation-reduction reactions, or redox reactions, they can be a lot trickier to balance. It is often very difficult, next to impossible, to balance these reactions by using sort of the inspection, guess-in-check method, because there's actually a lot of moving parts when it comes to chemistry that's being done, electrochemistry being done in the aqueous phase. So you can see here on our screen we have our balancing redox reactions, and you can see I've got a little bit of an algorithm here, a step-by-step process by which we're going to do this balancing. So what I'm going to do is, you have it all on one piece of paper. I'm going to zoom in towards the bottom to the two sample problems, and I'm going to work us through step by step how to handle balancing under two different kinds of conditions. We have to talk about how to balance a reaction under acidic conditions, which says right in the notes, where does it say acidic? Oh, it doesn't actually say it. So acidic conditions is one set of options we're going to have, and then we're going to have basic conditions as a second option. All right, so you will usually be told if the reaction is being done under acidic or basic conditions. And as you can see here, our first example is going to be under acidic conditions, and our second example is going to be done under basic conditions. The good news is it's really the same process, except for when you get to one additional step for basic solutions. All right, so I'm going to go ahead and zoom in on the first practice problem down here. Now, when you do this balancing, you've got to kind of keep track of your white space, and you're going to see that I'm going to start my problem solving by writing in the middle of the page, and I'm going to be adding things to both sides. So I'm going to start in the middle here, and I'm going to add things to the sides of reactions as I go forth. Okay, so the first thing we need to do is assign oxidation states to all the atoms. Now I'm going to jump forward just a little bit, and I'm only going to zero in on the things whose oxidation states change. So I'm going to quickly identify that the oxidation state of chromium here is +6. The oxidation state of the sulfur is +4. The oxidation state of this chromium is, of course, +3, and the oxidation state of this sulfur is +6. Okay, now I went through that pretty quickly, but you should be really good at assigning oxidation states at this point. All right, so now the next thing we're going to do is we're going to write what we call half reactions. So one half of the reaction involves the oxidation, and one half of the reaction involves the reduction, and we're going to write those as two separate processes. All right, so the reduction half reaction involves the chromium. So we're going to have the chromium Cr2O7 2-, and that is going to form the chromium 3+. And so we'll go ahead and we'll balance this half reaction first, and then I'll write the other half reaction. So the next step is to balance everything that isn't an oxygen or a hydrogen. And so in order to do that, I have to put a 2 in front of the chromium on the right. Next, we need to balance the oxygens by adding H2O to the appropriate side. So you can see I have 7 O's on the left, no O's on the right. So I'm going to go ahead and add 7 H2O to the right. So now my oxygens are balanced. I'm going to make the pen a little bit thinner so that I have enough space here. The next step is we're going to balance the hydrogens by adding H+ to the appropriate side. By putting in water, I've messed up the hydrogen. So now I've got 14 H's on the left, no H's on, 14 H's on the right, no H's on the left. So I've got to go ahead and add 14 H+ to the left. All right, so the next thing to do is to balance the charge by bringing in electrons. All right, so this is redox chemistry after all, so electrons are going out of the oxidation and into the reduction. So I can figure out how many electrons I'm going to need by taking a look at the charge. So on the left-hand side, I have 14 plus minus 2 for a total of 12 plus on the left. On the right-hand side, I have just the 6 plus. So electrons, of course, are negatively charged. So I'm going to need to add 6 electrons to the left-hand side. So let me go ahead and do that. So plus 6 electrons to the left. All right, so now this half reaction is all balanced. It's ready to go, and what I need to do now is go ahead and set up the oxidation half reaction and balance that. So the oxidation clearly is going to involve the sulfur compounds. So I have SO3, 2 minus, going to form SO4, 2 minus. So I'm going to follow the same algorithm. Balance anything that is not O or H, and that in this case would be the sulfur, 1 sulfur, 1 sulfur. Next, balance the oxygens by adding water. I have 4 O's on the right, 3 O's on the left, so I need to go ahead and add 1 water to the left, H2O. All right, next, balance the hydrogens by adding H+. So I have 2 hydrogens on the left now, no hydrogens on the right. So I'm going to go ahead and add 2H+ to the right. Okay, so now I need to go ahead and balance the charge by bringing in electrons. So my charge on the left, I've got -2 on the left, and I have 0 on the right, -2 plus 2, so 0 on the right. So then I need to put in my negative electrons on the on the right-hand side. So I'm going to go ahead and add 2 electrons to the right. Okay, so before I continue, one of the things I like to do at this point is to check to make sure my balancing is making sense. And I can tell if it's making sense if I have added electrons to the left of the reduction and to the right of the oxidation. Remember, reduction involves the gain of electrons, so the electrons would be gained as reactants in the reduction. And oxidation involves the loss of electrons, so they would be a product of the oxidation. Okay, great. So now my next step is to equalize the number of electrons on between the 2 half reactions. All right, so I have 6 electrons involved in the reduction, 2 electrons involved in the oxidation. So what I'm going to need to do is I'm going to have to multiply everything in the oxidation by 3. So I'm going to go ahead and do that, and I'll do it by writing in red here. So that means I'm going to have 3H2O, 3SO3 2 minus, 3SO4 2 minus, and then that'll become 6H plus and 6 electrons. Okay, so now I can go ahead and add the 2 half reactions back to each other, and as I do this addition, I can start to cancel out like terms. So one thing that has to, absolutely, positively has to go away at this point is, of course, the electrons. 6 electrons, 6 electrons. One thing that will often go away at this point would be things like H plus and water. I have 6H plus there, 14 there, so that can become 8H plus. I have 3 H2Os there, 7 there, so that can become 4 H2O. All right, and so now I'm going to add the 2 half reactions together to write my final overall oxidation reduction reaction. And what I'm going to have is 8H plus, let's see, Cr2O7 2 minus, plus 3SO3 2 minus, goes to form 2Cr3 plus 3SO4 2 minus plus 4H2O. So let's zoom out on that so we can see the whole reaction there in the middle of the screen. All right, and I should be done, but I always like to check my answer at the end. So the number of each atom should balance on both sides, of course, and the total charge on both sides needs to balance. Let's start with the charge. I have 8 plus -2 minus 6, so that is a total of 0 on the left-hand side. Okay, no net charge on the left-hand side. 6 plus right there, 3 minus right there, so that is a net 0 overall charge on the right. So the charge is all set. Let's count the hydrogens. 8 hydrogens, 4 times 2 is 8 hydrogens. 2 chromiums. 2 chromiums. 7 plus 9 is 16 oxygens on the left. I have 12 oxygens plus 4 more is 16 oxygens on the right. 3 sulfurs, 3 sulfurs. So I know absolutely positively for sure that this reaction is fully balanced and ready to go. All right, so always check your work at the end. Okay, the second reaction involves doing the analysis under basic conditions, all right? And so just to keep this video a little bit on the shorter side, what I'm going to do is I'm going to kind of skip a couple of steps, and I'm going to go right to the part where I've got the whole thing balanced under acidic conditions. Because if you look up above, steps 1, 2, 3, 4, 5, 6, 7, 8 are all the same. So I'm actually going to work with this reaction as if it's done under acidic conditions. And so the answer I would have if it were done under acidic conditions, and you should work through this yourself to make sure you could get to the same spot, I would have 16H plus 4MnO4 minus plus 3 elemental leads to form 4MnO2 plus, plus 8H2O plus 3 lead 4s, and that would be it. All right, so let's center that. And so this would be my answer if it were done under acidic conditions. Let's just double check it and do our charge check and our number of atoms check. So in terms of charge, I've got 16 plus minus 4, so that is a total of 12 plus on the left. 3 times 4 is 12 plus on the right, so the charge is good. 16 hydrogens, 8 times 2 is 16 hydrogens. 4 manganese, 4 manganese. 16 O's, 4 times 2 is 8, plus another 8 is 16 O's. 3 leads, 3 leads. So I know this is good under acidic conditions. But of course, the problem asked me to solve this as if it were being done under basic conditions. Basic, I guess that would actually be blue, so maybe I should change it to blue. So now what do I do to convert this to a basic solution? I kind of like to think of this as if it were a titration step, right? So I'm going to sort of quasi-neutralize this acidic reaction, and I'm going to do so by adding however many hydrogen pluses I have on one side. I'm going to add OH minus hydroxide to both sides of the completed balanced acidic version of the redox reaction. So in a way, I'm going to kind of neutralize this H plus while I turn it basic over here on the opposite side. So let me show you exactly what I mean by that. So I'm going to go ahead and add 16 OH minus to the left and 16 OH minus to the right. Now, what does that do? Well, the 16H pluses and the 16OH minuses, they're going to come together to form 16 water molecules. And what that allows me to do is do a little bit more canceling out. Now I can take these 8 waters that were on the right, cancel those out, and cancel out with 8 of the 16 waters on the left. And so now, under basic conditions, if I were to rewrite my final answer, you should always write the final answer on one line, nice and neat, so it's real clear what your answer is. My final answer would be 8H2O plus 4MnO4 minus plus 3 leads go to make 4MnO2 plus 3 Pb4 pluses plus 16OH minus. So let's go ahead and center that guy. All right, and that should be my final answer. Let's just double check one more time. I have, in terms of charge, 4 minus on the left. 12 plus minus 16 is 4 minus on the right, so my charge is good. Hydrogens, 16 hydrogens, 16 hydrogens. oxygens. 8 plus 16 is going to be 24 oxygens on the left. I've got 8 there plus another 16 gets me to my 24 O's on the right. Let's see, 3 leads, 3 leads. So I now know for sure that this reaction is entirely balanced under the necessary basic conditions. I'm going to tell you one of the mistakes I commonly see when students are asked to balance redox reactions on a quiz. Often the case is one question will be for acidic, one question will be for basic, and students will forget to do this titration step, this 9th step to turn the solution from acidic to basic. So I always, like when I do these problems, I think it's a good practice. If you see that it's done under basic conditions, circle the basic, and maybe at the bottom of the page or at the bottom of the workspace, write basic so you remind yourself to convert the solution over to basic. Okay, so that is balancing redox reactions. We've got some worksheets for you to do to practice this stuff. Believe me when I say you have to practice this. This is not a hard thing to do, but there are a lot of steps, and it's not that hard to make kind of a goofy mistake. And one mistake in the problem solving, you do, for example, in this problem here, if you do a mistake way back up here or up here, then that mistake is going to go through the rest of the problem, and you're going to have a hard time finding where you went wrong. So follow the algorithm, do the practice, and you'll get really good at this idea. All right, that should do it for now.